There we go. So like I said, first thing we are going to talk about today is absolute convergence. So a series, the sum n equals 1 to infinity of a sub n is absolutely convergent if the series n equals 1 to infinity of the absolute value of a sub n is convergent. And then this is helpful because if a series is absolutely convergent, then it is convergent. So we're not going to go through a whole proof of this, but just like kind of talking out like intuitively, why does it make sense that if a series is absolutely convergent, it is also convergent? Yeah, Rob.
Is it because absolutely convergent is a stronger claim?
It is a stronger claim. And it's a stronger claim because of negatives, right? So if all our a sub n terms were positive, these would be the same series. If all our a sub n terms were negative, whatever we got would just be like the opposite. Because if they were all negative, then the absolute convergence would just give you the positive, whatever it converged to would be the positive number of whatever you get when you look at the other series. And then if you have a mix of positive and negatives, right, that negative one is always going to be less than the positive one. So just as kind of like a hand wavy proof, that's why this is true. So it's a stronger claim. The ratio test tells us if we have a series n equals 1 to infinity of a sub n, then there's a couple things we're going to look at. So for each of these, we're going to look at the limit as n approaches infinity of the absolute value of a n plus 1 over a n. And then if this is less than 1, then the series is absolutely convergent. And thus convergent. If the limit from over n equals infinity of a n plus 1 over a n is greater than 1, then the series diverges. And what's the last case we need to write out? Equal to 1. Any ideas what's going to happen there? Inconclusive. Perfect. So if the limit of a n plus 1 over a n equals 1, then the test is inconclusive. And you would have to use some other test to show. We're not really going to run into this one because we're going to utilize the ratio test with power series. So it's not going to be an issue. Those are the 3 cases of the test. So let's go ahead and work an example together. So we want to determine if the sum from n equals 1 to infinity of n over 5 to the n is convergent, divergent, or if it's inconclusive. Okay, using the ratio test, I'm going to take my limit as n approaches infinity of the absolute value of a n plus 1. So everywhere I see an n inside my series, I'm going to replace it with an n plus 1. So I've got n plus 1 over 5 to the n plus 1. And then in my denominator, I have just n's. Now, you could try to simplify looking at it like this. This is very hard for me to understand what's going on personally, right? So what I like to use is my fraction trick that tells me if I am dividing by a fraction, what can I do with that fraction to get it out of the denominator? Flip it. Yep. From, let's see, like elementary school algebra, keep it, change it, flip it. So I've got n plus 1 over 5 n plus 1 times 5n over n. Okay. What do you guys want me to do? Yeah, so I have 5n over 5n plus 1. And then if I cancel out like 5n of those, right, I'm left with n plus 1 over 5 times n. Anybody know what this limit is? Yeah, 1/5, which is less than 1. Because the degree on my numerator and denominator was the same, my horizontal asymptote was a ratio of the coefficients in front of the highest degree thing. So I can conclude thus by the ratio test, the series from n equals 1 to infinity of n over 5n converges. So the ratio test does not tell us what this converges to. All it can tell us is that it converges. That's going to be good enough for us. Any questions about that?